Today we are going to learn the topic magnetic domain. So let's get started. So first over here, the domain theory was proposed by a scientist called named Weiss. So there are the few postulates of the domain theory given over here. So now a ferromagnetic material is divided into the large number of the small regions called as the domain. When we have a ferromagnetic material and we have divided that into a large number in a small number of the parts, and that particular part is called as domain. It is written now the size of the domain is from 10 to the power minus 6 to 10 to the power minus 3 centimeter cube. Now each domain is separated from each other by a wall known as domain wall. The domains which are separated from each other, that is called as a domain wall. In each domain, the magnetic dipole moments are aligned in same direction. Now in the domain, the magnetic dipole moments are present, so they are aligned all in the same direction. The magnetic moment varies from domain to domain and net magnetization is zero. So they have said the magnetic moment get changes from domain to domain and their net magnetization is zero. So let's see further. Now in the absence, now we're going to see in the absence of the external magnetic field. So in the absence of the external magnetic field, the domains are randomly oriented so that the magnetic dipole moments cancel to each other and the material has zero magnetic moment. So now here in this they are saying that when the domain does not contain any external magnetic field, or in the absence of the magnetic field, all the magnetic dipole moments cancel each other and they have the zero magnetic moment. Now the following is the figure of ferromagnetic domain in the absence of the magnetic field. So the further diagram shows you the this is the domain diagram in which no magnetic field is applied to this. So they are all in opposite direction, so we can see that the upward and the downward domains cancel each other, the left and the right domains cancel each other, and their net magnetization is zero. So over here we can see that representation of the domains in the absence of the external magnetic field. So now next, when a magnetic field is applied, there are two processes which takes place. So when we apply a magnetic field, the two processes take place, that is the motion of the domain wall and the second is the rotation of the domains. So the first one is the motion of the domain walls. When a weak magnetic field is applied to a ferromagnetic material, the size of the domain with axis parallel to the field begins to grow, while the size of the other domain decreases and the substance is magnetized. So whenever you apply a weak magnetic field to any of the domain, the size of the one domain increases and the rest of the other domains size goes on decreasing. So this is what it says, and the substance magnetizes. So this process is called as the domain growth, and we can see it in the further diagram. See, whenever we apply a weak magnetic field, so you can see that the first domain is, the size of that domain is completely increased and other three domains are decreased because of the weak magnetic field applied. Now when the weak magnetic field is removed, it comes back to its original position. Now whenever you remove this weak magnetic external magnetic force or external magnetic field, it occupies its original position and it comes to in this direction. So it comes in this position again when you remove the weak magnetic dipole moment at that time. So it occupies its original position. In this position it will be occurred again. So let us see further. Now next we have seen the motion of the domain walls. Now we are going to see the rotation of the domains. So in the motion of the domains we have applied weak magnetic field. In the rotation of the domains we are going to apply strong magnetic field. So when a strong magnetic field is applied to ferromagnetic material, all the domains turn in the direction of the applied magnetic field and the substances become strongly magnetized. This is known as domain rotation. The domain and the magnetic moment do not turn to its original position when external field is removed. So whenever you apply the strong magnetic field to any of the domain, all the dipole moments turn in that direction. In before cases we have seen that when we have applied a weak magnetic field, like the dipole moments do not go in the same direction, but the one of the domain size increase and other decreases. But here all the dipole moments are oriented in the same direction, and when you will remove that strong magnetic field, it will not change its position, or it will not acquire its original position. It will be in the same after when you apply the strong magnetic field. So let us see the figure for the next clarification. Here when you apply the strong magnetic field, we can see all the dipole moments are aligned in the direction of the applied external magnetic field. So here you can see that whenever you remove the strong magnetic field, again it will not acquire its original position, or it will not go back to its original position. It will be the same after this. So this is the entire theory of the magnetic domain. I hope you liked it. Thank you.